afternoon, everybody, and welcome. I'm Shelley Schlicker, the Marketing Administrator for Teledyne Tekmar, and it's my pleasure to welcome you to today's webinar, Headspace Analysis for Household Interior Paint. Before we get started, I have just a few housekeeping items to address. We ask that you place your phones on mute during the webinar. If you experience any audio issues, please dial *0 and an operator will be happy to assist you. You can submit any questions and comments during the webinar by selecting the Q&A module at the top of your screen. You can type the questions at any time, but we'll hold off till the end to answer them. Also, this webinar is being recorded and will be available on our website in the next couple of days. Now I'd like to introduce our presenter, Tammy Reller. Tammy is the Applications Field Sales Specialist for Teledyne Tekmar.
Good afternoon, everyone. As Shelley just mentioned, I am one of the applications chemists, and I will be presenting some of the data today, and along with my colleague, Roger Bardsley, who's also an applications chemist. When I looked over the list of attendees today, I saw in the audience that we have quite a few that are analytical chemists, and we also have quite a few that maybe haven't been able to spend as much time in the lab, or they're just trying to get some initial information. So I want to start off this presentation by talking a little bit about the theory on Headspace, some of the basic concepts that deal with static Headspace analysis. I'll spend a little bit of time going into some more in-depth discussion of the chemistry behind it. So to start off, what exactly is static Headspace analysis? This, to me, is one of the most versatile techniques on the market today. It is used for the concentration and analysis of volatile organic compounds in a wide variety of matrices. It is also one of the best techniques that can be used for method development and can provide sensitivity very similar to that of dynamic purge and trap. And the reason for this is that there are so many different types of sample matrices, and there are so many different types of analytes that we may be looking at. And static Headspace gives us the ability to have a direct influence or a direct impact on some of those sample matrices and whether or not we are able to get those analytes out of solution and into the headspace. And we'll be going into a lot of these different parameters later on of how you as an analytical chemist can directly influence the sensitivity of your analyses. I want to take a couple minutes just to go and do a brief overview of what the difference between dynamic headspace and static headspace is. When we talk about dynamic headspace, we're referring, it's just another term for purge and trap. And if you look at, let's see if I can get a pointer here. If you look at this top diagram right here, which looks like a purge vessel, you can see in purge and trap, we send a carrier gas such as helium in through the sparge vessel, and it's going to come up and it's going to purge through our matrix. Generally, in environmental analysis, that matrix is either water or wastewaters, and in some cases, soils. As you can see from the graph over here, we are actually, in purge and trap, the idea is to get a 100% recovery of the analytes. So when we send the helium through, typically we may purge a sample for, let's say, 11 minutes at 40 mils a minute. And in optimum conditions, if you have a lot of volatile analytes in that solution, we should be able to purge most of those analytes out. Hence, when you get over to this graph, you can see that over time, the more we purge, the more the analytes will come out of solution and into the heads and be able to be transferred over to the GC. And eventually, the reason this graph is coming down here is that we are getting a 100% recovery of those analytes. The idea is that we purge and get as much of the analyte out of that matrix as possible. Now, when we come down to static headspace analysis, we talk more in terms of equilibration. You have a concentration of a sample matrix and the concentration of the gas phase. And as you can see by the graph here, as you increase time, you are actually increasing the concentration in the gas phase. And eventually you will meet a plateau. And this is where we talk about the equilibration or the equilibrium time. This is where we are getting where the amount of analytes leaving the sample matrix is equivalent to the amount of analytes returning to the sample matrix. Or in other terms, the amount of analytes in the sample are equivalent to the amount of analytes in the gas phase above that sample. You can see the dotted line as we're going down here at the back end of the graph. And generally, that could mean that if you are equilibrating a sample for too long of a time, those analytes may end up returning back into solution. This is just a picture diagram of what we're talking about when we talk about static headspace equilibrium. All of these little red X's represent the analytes that are in your original sample matrix. And over time, at a certain temperature, the rate of those analytes leaving the sample matrix and the rate of analytes returning will be at what we call static equilibrium. And that is the most optimal condition that we want to be able to sample this headspace and be able to send that over to GC for analysis. So what are some of the reasons why one would use static headspace for their analysis? It can be used for both qualitative and quantitative analysis. In terms of quantitative analysis, we would start with an initial set of standards, be able to put a certain amount in the vial, and then we would be able to quantitate that based on relative response or area counts. From a qualitative standpoint, it might be a situation where you have a sample, an unknown sample, and that comes into you and you have no idea about the chemical qualities of that sample matrix, and you really have no idea what you're looking for in that matrix. In this case, it can be just a qualitative analysis where we put that sample onto the headspace and get an idea of what it is that we're possibly looking for. It also gives us the ability to assay a variety of sample matrices. When we talked earlier about purge and trap, you're generally looking at regulatory methods, drinking water, wastewater, soil, and these are all methods that have been used over the years to analyze VOCs. When you get into Headspace, it gives you a whole different variety of samples that you can look at. In cases we're looking at coatings, we can look at residual solvents in pharmaceuticals. We can look at food and flavor compounds, polymers. That's another area that's really popular with high temperature headspace. It's very difficult to analyze polymers any other way. Blood. A lot of times headspace is used for blood alcohol analysis. And also it is sometimes used in the environmental labs, such as analysis of soils. In some cases, people will use headspace to pre-screen their soils to make sure that they are at not too high level of concentration prior to putting them on the purge and trap. The other thing is we can analyze solid samples directly. In the case, most of the time you would have to do some type of extraction of those solids prior to analyzing them. That might be crushing them up. That might be trying to dissolve them in some type of solvent. You might have to do an extraction of that. Now with Headspace, we can put solid samples directly into the vial and use temperature and a wide variety of other parameters to analyze those analytes directly. It enables us to evaluate or look at high concentration samples. In the case of a purge and trap, you're pretty much limited to the ppb level. When you get into static headspace analysis, you're only sampling the gas. You're only sampling the headspace above the sample, so it's a very clean analysis. So in cases, you may end up being in the very high ppm range. We're going to talk a little bit later about increased sensitivity, so I'm not going to go into a whole lot of that now, but you are able to use heat, time, matrix modifiers, pH. There are a lot of different variables that the analyst can actually do different things to either the sample matrix or the actual method in order to increase the sensitivity. So overall, we're saving time and money by not having to do extraction and concentration techniques, and we're minimizing time because we're doing direct sampling of that headspace. We're not having to go off and do an offline extraction of a solid and then put that in a vial and analyze it. We're able to put the solid directly in there and analyze. For those of you that are not familiar with static headspace, in generally, you take some type of sample, it might be a liquid, a solid, and you place it in a sealed vial. That vial is typically heated to a certain temperature for a certain amount of time. The volatiles will leave the sample matrix and migrate into the gas phase, and this is called the headspace. The headspace is then sampled and sent over to the GC or the GCMS for analysis. Since we're sampling headspace, this is why it is such a clean technique, because you're only sampling the gas phase. Now this is a picture diagram of static kind of headspace theory in the vial of what actually is happening. If you look down here, this is the original mass distribution that is in our sample. And as we apply time and heat, these analytes will move out of the sample phase and into the gas phase until they reach what we call equilibrium. We're going to talk about many ways to influence the movement of these analytes out of the sample matrix and into the gas phase in a little bit. So let's talk a little more about this picture, mass balance equation. When a sample reaches equilibrium, the mass in the matrix, that's this original mass distribution down here at the bottom, hopefully you'll be able to see my little red pointer moving, plus the mass in the gas phase must equal the original mass placed in the vial. Now, there are many factors that we can have a direct influence on in affecting the sensitivity. These four factors are why static headspace can be such a powerful method development tool. In most cases, the analyst will have some knowledge of the sample matrix they are looking at and what types of compounds they are looking for. When we talk about phase ratio and partition coefficients, these two generally work together in combination. So what is the phase ratio? The phase ratio is defined as the relative volume of headspace compared to the volume of sample in the vial. We can look at it in an equation that the volume of the gas divided the volume of the matrix is going to give us what we call this phase ratio. And you'll see in a few minutes how that's really important on affecting the sensitivity of the analytes that you're trying to get out of that matrix. The way you find the volume of the gas is you take the volume of the vial. In most cases, that size will be 9, 12, or 22 mils. Those are the most common sample vial sizes for headspace analysis. Subtract out the volume of your matrix, and that's going to give us the volume of the gas. So let's look at an example of a phase ratio. If I have a 22 mil vial and say I put 11 mils of water into that vial, that will give me 11 mils of gas. So the actual phase ratio, remember we said it's the volume of the gas divided by the volume of the matrix. So if I take 11 mils divided by 11 mil samples, that's going to give me a phase ratio of 1. Let's take another example. If I have a 22 mil vial and I'm putting a very small sample size in, such as 2 mils, that gives me 20 mils of gas. That makes my phase ratio very high. That gives me a phase ratio of 10. Another example is if we put in a very large sample volume. We have a 22 mils headspace vial. We're going to put in 22 mils of water. That gives us very minimal. That just leaves us 2 mils of gas above that sample for sampling of the headspace. That gives us a phase ratio of 0.1. So how does that really help us when it comes to sensitivity? The idea is that we want lower phase ratios, meaning a larger sample size. This is going to help us yield a higher response for volatile compounds. So the last example I gave you, where we had a 22 mil sample vial, and we took and put in 20 mils of volume, that should give us a greater increase in our sensitivity. Why is that? That is because the more matrix you have in there, the more volatiles or the more analytes that you may have in there to be able to move into the headspace. But no, decreasing these values does not always yield an increase in the response that you need to improve sensitivity. So let's take a look at partition coefficients. Remember earlier I said that phase ratio and partition coefficients usually work in combination together to help increase sensitivity. So we need to take a look at that and have an understanding of how partition coefficients work in the sample matrix. We define the partition coefficient as the ability of the analytes to partition between the sample phase and the gas phase. So basically the concentration of the sample divided by the concentration of the gas phase is going to give us our partition coefficient. In layman's terms, what we want to know is how easy is it for those analytes to migrate out of the sample matrix and get into the gas phase for analysis. You will have some analytes that never ever want to leave the matrix. These are typically your polar compounds. They're very happy where they're at in that sample matrix, and it takes a lot to be able to get them to move out of that and into the gas phase. You also have analytes that don't like where they are, and their job is to move readily out of the sample matrix and into the headspace. These are going to be your nonpolar or your most volatile type compounds. So compounds that have low K values will tend to partition more readily into the gas phase and have relatively higher responses and low limits of detection. I'm going to take you back back to this slide here. When the concentration in the gas phase, which is this bottom number, when that number is high, you are going to have a lower partition coefficient. So you can make the analogy there that those are the types of analytes that they want to get out of that sample matrix. They want to move it into that headspace. So samples that have low partition coefficients are going to be the easiest ones to analyze. Those that have higher K values or higher partition coefficients, they generally give us a lower response. They are very soluble. They do not want to leave the sample matrix that they're in. The interesting thing is that now you can have, with Headspace, you can also have an effect on the partition coefficients. Some examples of that are temperature. We can change the salinity of the solution by using matrix modifiers. We can change the pH of the solution. And I'm going to go into each one of those a little bit in a few minutes. But I want to take a look at this next slide so you can get an idea about low K values and high K values. So if we look at some of these typical partition coefficients for organics in water at 50 degrees, you can see on the top the paraffins up here. Your pentanes, your hextanes, your heptanes, they have very, very low K values. They do not want to stay in that water. They want to move out, or whatever your sample matrix is. But in this case, we're looking at water. They want to get out of that water and into the headspace. Now, when we look at methanols and nethanols, those are very polar compounds. They like where they're at. They have no desire to get out of that sample matrix. So there are things that we can do to have an influence on these types of compounds that do have higher K values to get them to move. So let's take a look at a couple of those. The first thing that we can do when we have a compound that has a high K value, in this case, let's pretend that we have methanol in water. and we need to find a way to, that methanol does not want to leave. It's very happy where it's at, so we're going to use a matrix modifier. We're going to add some type of salt that's going to help modify that solution, and it's going to reduce the hydrogen to hydrogen bonding, which will make it easier for the analytes to move out of the liquid phase and into the gas phase for sampling. Some of these types of salts are ammonium chloride. One of the most common is sodium chloride that is used a lot of times. And what that will do is by adding that sodium chloride to it helps to reduce the partition coefficient of A, making it go into the headspace more readily. Sodium sulfate, potassium carbonate, those are another couple examples of matrix modifiers. Another way to influence the K value is adjusting the pH of the sample. Certain compounds tend to be more or less volatile depending on the pH level. An example of this is pyridine. At low pHs, pyridine is relatively a non-volatile compound. At a high pH, it can be a relatively volatile compound. So this enables the analyst to modify the sample and help pull those analytes out. And in some cases, you may need to suppress an analyte. There might be other things, it might be overpowering the headspace. So you're able to change the pH, which basically changes the volatility of that analyte, so you can allow some of those other compounds to move into the headspace. And the last, derivatization. This alters the partition coefficient basically by changing the chemical structure of that compound. So let's take a quick review of phase ratio and partition coefficients. These two play an important role together to help increase the sensitivity or response to those compounds. The lower the phase ratio means we have a higher sample volume and we're going to be able to increase our response. The increase in the sample size is only effective if you're dealing with a low K value, a low partition coefficient. This means that the analyte is less soluble and will give you a greater response. With analytes that have a higher K value, no matter how much sample you put in that vial, if those analytes are happy where they are in the matrix, they're not going to move out of there at all, no matter what you do. So we talked about phase ratio and partition coefficients as an effect on sensitivity. Now I'm going to move into a little bit about temperature and heating time and how those can have an effect as well. Once again, we see this K value again. By increasing the temperature of the sample in the vial, it helps us to lower that K value. This can have a great effect on your headspace analysis. You're increasing the amount that's released into the vapor phase of your target analytes. You can also have some adverse effects of temperature. One thing to keep in mind is that when we're doing some method development and looking at temperatures, you want to keep in mind, in some cases you will not know what the boiling point range, because you may not even know what the sample matrix is that you're looking at. It might just be some unknown. But in cases where you do know, you want to keep the temperature about 15 degrees below the boiling point of the matrix. If not, once you get closer to the boiling point of that matrix, let's say water boils at 85 degrees Celsius, you want to keep any analysis 15 degrees below that. Otherwise, you get to the point where you could blow off the caps of the vials, or you might get some bulging, in which case your analytes are going to leak out and under the septa. In some cases, you might end up, if you heat the sample too high, you might also get some sample degradation of thermally labile compounds, in which case you're going to get a reduced response. So these are just two things to keep in mind. I know a lot of people think, well, I'm just going to put it in there and ramp it up to the highest temperature that I can. But there really is a systematic way about going and figuring out what is the optimum temperature that will put us in that equilibrium state, so we're not on the front of the curve where maybe our temperature is not high enough to give us the response we're looking for, but we also don't want to be at the back end of that curve where our temperature is so high that we are now degrading our sample. The other thing that works in conjunction with affecting sensitivity and temperature is the heating time. I'm going to go back to this original slide I showed, and where we're looking at we talked about the analytes leaving the matrix is equal to the analytes returning to the matrix. And what I want to do is highlight this area right here. This is where you want to be. This is going to be your optimum response. We talked about if you do not heat the sample long enough, you're going to end up on the front end of this curve where you're not getting maximum response. If you heat the sample too long, there is the possibility of some of this analytes returning back into the sample matrix. If they're sitting there for way too long, they will have reached equilibrium, and now they can come back down and move back into this matrix. You can also change this variable right here to include temperature. As we increase the temperature of our sample going up this curve, we're eventually going to hit this plateau. So this is the reason I keep going over this, because this is probably one of the most important equations in static headspace analysis. This is where you want to get, where you want to be right here in this equilibrium to get maximum response. Now this is from our software, and it gives you a list of things that we are lists of parameters that we are able to optimize in static headspace. The one thing I do want to point out at the top here is constant heat time, and that is critical because you want to make sure that every sample is heated to the same temperature for the same amount of time, so that you know that that's where you're going to get your most reproducible results. And in the software, you're able to plug in the GC cycle time, and this enables you to heat up to 10 samples at one time, and so that as soon as that equilibrium is reached, you know that the GC is ready and it's ready to sample, so that none of those vials are sitting in that platen longer or shorter than any of the others. We're going to go through a couple of these headspace parameters to talk about the best way to optimize your method. In the HT3, we have what we call a method optimization mode, and it enables us to automatically change these parameters within the software. So this is what I was talking about earlier as far as method development. You know, it used to be that we would have to put a sample in and we'd run it at 65. Then we'd have to change our method and run it at 85 and change it again. The software enables you to set up all of these methods, and you can load up all of your samples, and you can change the time, you can change the temperature, you can change the vial pressurization, the mixing, the loop fill pressure. You're able to change all of these variables by setting up different methods and walking away, and then coming back to analyze your data to find out what are the optimum parameters for each of those. Now, when we talk about valve and transfer line temperatures, you want to set those slightly higher than what your sample temperature is going to be. And this helps to eliminate any cold spots in the system. So say we're going to analyze, we're going to put our sample at a temperature of 85 degrees. And that's what we want to set it to, and that's what we're trying to reach our equilibrium at that temperature. You generally want to set those valve and transfer line temperatures higher. It helps to keep the system clean. You definitely do not want any cold spots. Some of the most critical characteristics in a headspace are that you need to have inert sample pathways. So let's talk a little bit about what vial pressurization is. When we take the sample, we put our sample in the Headspace vial, we're going to crimp it and we're going to put it on the analyzer. The sample will generate what we call a static vial pressure. And this is different for all different types of sample matrices. Some have higher static vial pressures, some have smaller static vial pressures. But it is important to be able to figure out what that is. So generally, if you have no idea what type of sample you're running, we can put three samples on the system and just run it through on an average program. This is then monitored. Oops, sorry, I forgot to change my slide. This is then monitored in the system history through the mass flow controller. You can go and pull up the sample and say that sample 1 at this time and temperature gave me a static vial pressure of 7. And you can go further down into your list and look at different vials or different samples that you have run. In order to get the Headspace out of the vial and into the sample loop, it's going to pressurize the vial with helium. We generally want to set this 2 to 4 psi above the static vial pressure. You don't want to have too high of a pressurization in there because since it's actually pressurizing the vial with helium, you could possibly dilute your Headspace. Another parameter that we're able to do in our method optimization mode is sample mixing. This helps to increase the gas to liquid interface in the vial, thus reducing the distance the analytes need to travel to reach the gas phase. For example, in mixing of soils, sometimes when you're looking and you're trying to pull volatile organic compounds out of a soil, you will add some type of methanol or extraction solvent. If you mix the sample for a little while, it helps to increase the surface area interaction and is going to help those analytes move out of solution and into the Headspace at a much faster rate. Therefore, you may end up being able to reduce the overall thermal exposure time needed for the sample to reach that equilibrium. Let's talk a little bit about sample loops. The volume of the sample that is transferred over to the GC is usually controlled by the size of the loop. All the Headspace and the HT3s are shipped standard with a 1 milliliter loop. They come in different sizes. They come in 100 microliter, 250, 500 microliter, 1, 3, and 5 ml. So obviously, the larger the loop, the more sample you will get on column. This is another error where somebody may send you in a sample where they have no idea what the concentration, but you may think, well, this could be a very high ppm sample. You don't want a large sample loop for that, because then you're going to be transferring a lot of compound over to the GC system. One way to do kind of theoretically a dilution of that is to put in a smaller loop size. But due to the increased sensitivity of changing the loop size, I mean, this is kind of like temperature. When we talk about temperature, we don't automatically want to run it to the highest temperature to increase our sensitivity. And it's the same thing with the loop size. We don't want to automatically go to the largest loop so that we can transfer the most amount of volume over. We want to work on some of those other parameters, the phase ratio, the partition coefficients, the temperature, the time. Those are things that we want to optimize first prior to putting in larger sample loops. Now, in a few minutes, Roger's going to come in and he's going to talk about how he optimized the paint method. And these are the two things I just want to touch on, because the parameters that we looked at primarily were optimizing the sample temperature and optimizing the sample equilibration time. With sample temperature, the higher temperatures tend to shift the equilibrium to favor the Headspace. Remember, especially when the high K values are involved, if you add more temperature to the vial, going to lower that K value and help those analytes get into shift the equilibrium in favor of the headspace. The other thing that we also talked about that the temperature is limited by the boiling point of the sample solvent. You want to keep that sample temperature 15 degrees because you don't want to be blowing those lids right off the caps of right off the vials. And if you have any thermally labile components that might degrade because of the temperature, you need to take this into consideration as well. So last, let's look at the equilibration time. This is always dependent upon the type of matrix that you have, the analytes you're looking at, and the temperature. The amount of time the sample has to equilibrate at a particular temperature is totally dependent on these three items. At equilibrium, the analyte concentration is at a maximum. And so sometimes putting that sample in a vial or heating it for a longer period of time may end up, it's not going to change the way that those analytes move into the headspace significantly. And here comes our favorite slide again. And I just want to reiterate this, and the reason is that this is, like I said, this is a very important equation for static headspace. And so this is the optimum time that we want to reach right here. This is the area where leaving a sample in the platen for a longer period of time might get to a point of no return. In which case, then you're just losing time, valuable time and money. So let's review a little bit that some of the reasons why Headspace is one of the most versatile techniques on the market. It gives the analyst the ability to change a wide variety of parameters and influence the sensitivity of those analytes. The advantage of the HT3 is that it can automatically do most of this work for you in the software. So now that I've given you a brief chemistry lesson, let's move on and talk about the paint. So I'm going to turn it over to Roger now. Roger did all of the work on the Headspace Analyzer for the paint samples, and he is going to go into greater detail about how he actually set up the method, and you will be looking at some chromatograms and data from that.
Thank you, Tammy. First of all, I'd like to go over a little bit of the history of paint requirements for low VOCs. The Clean Air Act was enacted by the EPA in the late 80s to early 90s. Some of the notable actions of this act that we know of are the ban of CFCs as propellants, catalytic converters, and the removal of lead from gasoline. Section 183 of the Clean Air Act includes regulation concerning the amount of volatile organic compounds for architectural coatings. And in 1999, that was at 250 grams per liter for flat paint and 380 grams per liter for non-flat paint. The section was updated recently in 2009 to incorporate something that the world has been looking at called the relative reactivity approach. Some states already have these rules in effect, so the EPA created this national rule to assist the manufacturers from the administrative, technical, and marketing nightmares created by these different state rules. It also assists the state regulatory agencies from issues associated with compliance problems created by potential non-conforming materials being brought across the state borders. Finally, some organizations have initiated a system to assist customers in their purchase of low VOC paints. Green Seal is one of these organizations that has some specifications. They have some limits for those, what they can and can't contain. They have a limit for a flat top coat of 50 grams per liter, a non-flat top coat of 100 grams per liter, and this all uses ASTM D68863 for monitoring these limits. Also, European nations have started with what's called the REACH code to help identify and lower volatiles and compounds that they don't want in their products to keep them out of the products. How do you create a method for a water-based paint? Well, first you obtain the various paint samples, then you set up a GCMS system, then you set up some initial headspace parameters, then we use M.O.M to build a method by varying the headspace sample temperature and varying the sample time that the samples see. We obtained 5 paints that were commercially available at a local home improvement store. The pre-2009 paint had already been previously used and resealed, so some of the volatiles may be lower than an unopened can. The post-2009 paint was the same label grade as the pre-2000 paint. For people that understand paint, there are different grades that have different sheens, different durability, different polymers and things that make them last longer. We also used a sealing paint, which was a different formulation with different polymers. We also picked up acrylic vinyl chloride paint that was labeled as a low VOC paint. It had acrylic polymers and ethylene glycol in it and a vinyl chloride polymer. Finally, we picked up a low odor, no VOC paint that was a vinyl paint that is a newer paint on the market to meet the low VOC demands. Setting up the mass spec, we used our Thermal Focus GC DSQ2 mass spectrometer. We put it in split mode with an inlet of about 260 degrees and a 30-to-1 split. We monitored the effluent and the mass spec from 29 mass units to 350 mass units with a source temperature of 200 degrees. The transfer line from the GC to the mass spec was set at 260 degrees. For the separation, we used an RTX VMS column, which does a very good job of separating out volatiles. It was a 20-meter column with a 1 micron film thickness. We set it at a constant flow of 1 mil per minute, and the temperature profile for these materials was 35 degrees C for 1 minute, ramping to 260 degrees C at 8 degrees per minute, and then finally holding that at 260 degrees. To set up the headspace, we picked some basic parameters. We put the valve oven and transfer line temperature at 120 degrees. To pressurize each vial, we set that at 15 psi's. We used a 1 mil loop. We filled that loop to 10 psi's, and the sample size was only 500 milligrams. We would weigh 500 milligrams into the vial, cap it, and put it in the headspace analyzer. We then used M.O.M to create the various steps for the sample temperature. We started at 65 degrees and went up to 185 degrees in 10 and 20 degree steps. An example of that is here, where we first picked a method, then we set what we wanted to change, we set the start temperature, the step value, and then the number of steps we wanted to take. We then told it the number of vials that we wanted for each step, and that created this method, the methods here that you can see on the left. After that was performed, we went back at each temperature and looked at just the data for the pressure in each vial. As you can see from this table, from 65 to 185 degrees, the pressure varied quite drastically. We stopped the analysis at the 165 degree run because that is at the limit of our system of 30 psi. The 185 degree temperature would have erupted the vial and caused a mess in the headspace. Here's a photograph of a vial at 145 degrees and the same paint sample at 165 degrees. You can see the pushed up crimp seal and the paint that has spewed out at 165 degrees. That would indicate a loss of samples. Now let's move on to the paint samples that we did. First, starting with the no VOC paint, here are the different temperature chromatograms that we see. As you see at 165 degrees, we get some overloading. Two ways you can take care of that is to increase the split or change column size. One thing the higher temperature does do is it helps drive the ethylene glycol and the propylene glycol into the headspace. We also think we saw acetic acid. It could have been ammonium acetate. We weren't sure because the hits with the mass spec system were similar. If it was, we'd have to add some to the formulation to confirm whether this was acetic acid or ammonium acetate. But again, this is something you don't see at the lower temperatures below 145 degrees. As you get to that higher temperature, as Tammy was pointing out, you can force some of these compounds up into the headspace. Why could we go to 165 degrees? That's because of the amount of minerals and other materials in the paint that increases the boiling point of the paint well above 165 degrees. You'll also notice at the higher temperatures we do see two humps, what we call highly unresolved multiple peaks, at around 14 to 17 minutes and 22 to 27 minutes. This could be a higher boiling point compound in the formulation, but we're not paint formulators, so we're not sure. If you wanted to analyze for it, you could probably do some different parameters to get those better resolved. Moving on to the low VOC paint, the one thing you'll see is this paint has a little different formulations from the fingerprints of the peaks that we see. Also, you'll notice at approximately 16 minutes, this peak here decreases as the temperature increases. And that's what Tammy was pointing out about. It's important to figure out the equilibration of these compounds. Moving on to the ceiling paint, again, a little bit for formulation. We see the overloading again this time, not only of the peaks in this area here, but also of these two component peaks in this area. As you can see, with the rounding and the change of the ratio of the two peaks at the 165 degrees. Also, we see a possible water effect where, again, we can't keep the water out of the sample through static headspace, so it can cause some effects in the early eluting compounds, causing them to broaden. Now I'd like to move on to the pre-2009 paint. Again, this is one that has a very high VOC content. We still see overloading in this one. We should also still see the humps, which again, we're not sure if this hump here is overloading or is it other compounds. We also see ethylene glycol, the acetate, there's acetic acid here. And one thing I'd like to point out is we're going to be looking here later at this peak at 8.5 minutes, how it changes versus time, along with the peak at 19.2 minutes. As you can see, it's not observed in the 65 and 85 degree samples, but when we get up to 105, 125, and 145, we see it, and then 165, it gradually disappears. Now I'm going to switch to the post-2009 paint. The one thing I want you to see is the drastic change in the ethyl or the glycol ether peak at 16 minutes. It's almost non-existent in the post-2009 paint. So this is a formulation change that the manufacturer made to meet the requirements of the 2009 Accord. Also, you see the peak at 20 minutes overloading as you get to 165 degrees, indicating too much sample in the headspace or onto the column. Now, we have a temperature idea. We have 6 temperatures. How long should we expose the sample to those temperatures? So what we did was take a couple of the peaks from the different paints and graph them in terms of the peak area of that peak. From this data, you can see that an optimum temperature for these samples would be around 105 to 125 degrees. Our next step would be to go ahead and set up another run using this data. We chose 125 degrees for the peaks with lower concentrations. That's when they were starting to come up above the baseline. We then used M.O.M to vary the sample equilibration time. We set the GC cycle time this time for constant exposure because we wanted to make sure that when we told it to be in there for 15 minutes, the sample only saw 15 minutes of heat. Again, to set that up with M.O.M, we set up a method. We chose sample equilibration time. We started at 15 minutes. We stepped the values at 15 minutes per each step. We wanted 5 steps to get to 75 degrees, or 75 minutes. And we had 7 samples per each step. Again, once we clicked apply, it set up the entire method for us. We put the vials in and pushed the run button. Going back and looking at the paint, first thing we would like to look at is the vinyl paint again, which had no VOCs. From this, you can see a compound missing as you move up through the time. This could be due to loss of headspace equilibrium, or it is a thermally liable compound. Another interesting phenomenon we observed was the aliphatic amine moving through the retention times. Again, this retention time shift could be due to the headspace equilibrium issue, or it could be reactivity. We're not sure, and that would require further analysis to determine that. Moving on to the low VOC, again, you see the aliphatic amine moving through the sample. With this sample, the peaks do not vary much versus time. So for this sample, by placing it in the Headspace system for 15 minutes, you could get the same data as if it were there for 75 minutes. Moving on to ceiling paint. Again, this is another paint that's very stable, and we didn't really see any peaks increasing or decreasing over the unit time. To the pre-2009 paint, similar results. Not a lot changed. The peaks all stayed there. We didn't see any increasing peaks or decreasing peaks. When we moved to the post-2009 paint, one of the peaks did decrease as we kept it in the platen longer times. The Headspace method allows us to quantitatively compare this data. First thing we did was to sum all the peaks, and we looked at a bar graph versus the label VOC. I want to reiterate that just because a peak is in the chromatogram does not mean it's a regulated VOC to the EPA. Then we looked at a single component comparison by using the peak at 16.4 minutes, the glycol ether, to show how drastically that was reduced in the formulations. This is the bar chart of the sum of all peak areas. The blue column is what was labeled on the can. That is a maximum amount that may be in the paint sample. Again, the pre-2009 paint sample had been previously opened, so some of the volatiles may have been less in that compound, or in that paint sample. Moving on to the single component. This is the one that drastically was reduced from 2009 to all the other formulations. This glycol ether was extremely large in the pre-2009 paint. The other paints had extremely small quantities of it in there. Moving on, for another part of the Headspace analysis is to compare the formulations. So we compared the 5 paint samples by overlaying them on the same scale. Then we expanded the region to look at lower concentrations. Here are the total ion currents of all the paint samples overlaid, which really shows some of the significant differences of the paint samples. The VOC paint here, as you can see, has very low concentrations of all components in there, including the lower alcohols and ketones, and moving up to the higher glycols. The low VOC also has some lower concentrations, but it also has different concentrations of the peaks in there. For example, this peak here is higher concentration than the no VOC. The ceiling paint, you can see a difference in the formulation right in this area here where it has additional compounds. And then when comparing the pre-2009 with the post-2009 paint, you'll see that this peak here has drastically decreased, and this solvent here is lower. I'd like to wrap up and talk just about some of the methods that the paint headspace method could be used for. For paint manufacturer, this could be used to check formulations to ensure the correct VOC compounds were added to the sample. For the paint manufacturer also, they could quantitate the VOCs on there to make sure the right amount was in there. In terms of stability, if the paint manufacturer wanted to change to a different supplier of the glycol ether, they could put the formulation in there and see if it affected anything else in there. For the environmental issues, in terms of a regulatory review, for example, REACH in Europe is restricting what some samples can have in it. So this would be a way to determine if outlawed compounds were in the paint. It also could be a method for paint recyclers who take a look at the paint. If it had, for example, maybe benzene in it from a really old paint sample, they'd have to dispose of it in some other manner than what they're currently using. At this point, we'd like to do a summary of headspace analysis. It can be used for both qualitative and quantitative analysis. It has the ability to assay a variety of sample matrices, including coatings, pharmaceuticals, food and flavors, polymers, blood, and environmental soils. The solid samples can be analyzed directly. As with the paint, we just put that directly into the headspace file and put it onto the instrument. High concentration samples can be evaluated. Again, the paint has very high concentrations of volatiles. We can just put that in there directly. You can increase sensitivity with heat, time, and some matrix modifiers, and it saves time and money. In terms of some other HC3 applications, if you're interested in reading any of our applications, please visit our website at teledynetekmar.com/applications. You can find things for doing free screening for soils, residual solids for the pharmaceutical industry, and other applications.
Okay, that's the end of our webinar. We're going to open it up to any questions that you may have. So you can either type your questions and send them to us, or we'll open it up to the people on the phones as well.
We do have one question. This question, do I have to use helium for the analysis? If the GC requires helium, you can use the helium on the GC. The headspace unit does not require that. So you could use nitrogen for that application and save some cost in that helium.